So I'm Philipp. I work for Appearin. We're part of Telenor, the Norwegian telco, and we run the service called Appearin, and I'm doing all the WebRTC stuff there. And I want to talk about debugging tools and techniques for WebRTC and answering the question, what happened when a call went wrong? So WebRTC works great, usually, like 95% of the time, no, it's great. The video quality is awesome, the audio quality is good, and everyone is happy. Most of the time, especially when you test locally, because then you don't get packet loss. However, in production, calls fail. 1% or less, but they do. And people can't hear each other. We've seen Marcio saying that. And it's true, unfortunately. And there's a large desync, for example, between audio and video. We had that in February. And people describe the quality as horrible, whatever quality means and whatever horrible means. And let's not get me started on interrupt problems like Chrome and Firefox not playing well with each other, or Chrome not playing well with Microsoft Edge. And I've seen frequently browser upgrades breaking things. So every 6 weeks I see, oh, something broke. OK, great. If you want to read more about that, I have a blog on Medium and lots of stuff there. So you get user reports. They say, oh, the call failed. The audio is bad, or the video is bad. And then your product manager or your customer support person is going to ask you, what happened? So what do you do then? How do you answer that question? How do you figure out what happened? And maybe what action do you take? So let me show you some of the tools and techniques I use. So in terms of tools, there is, most importantly, Chrome's WebRTC internals page. Firefox has a page about WebRTC. And most likely, you will end up building your own solution or use a service like Varun's. So Firefox is about WebRTC. It is very basic compared to Chrome's page. It shows you all the connections that are currently active. It shows you the SDP. And it shows you how the connection is established. So it shows the ICE candidates and their state. Chrome's WebRTC internals page is one of the tools I use most often. It shows you API traces and statistics for all calls, for all peer connections. And at the top, you can see over here, you get all the connections, you get all the user media requests, you get all the connections, and for each connection, you get the configuration. And you get those API traces on the left side. They basically tell you all the peer connection calls that happen. And on the right side and at the bottom, you get the statistics, which are sent to the WebRTC internals page every second. And the API traces are really useful to figure out what happened in the call, like when was an offer created, did you get any set local description failure calls, and all that. And for example, you would call add stream on the peer connection, and it would show, oh, a stream was added, it had this label, it had this audio track, and it had this video track. So that might be important if you, for example, expect this to happen with an audio and a video track, and you only get an audio track here. For example, then the user might not have a camera. And you can see how the SDP offer is created with what options. Like here we are looking at something where we call it with offer to receive video and offer to receive audio. So we want to receive audio and video. And we can also see the set local description call, which shows you the whole SDP. It's a big blob of text. If you want to know more about that, there's a great WebRTC hacks post on that. And you can also see all the on-ICE candidate and at-ICE candidate events, which show you how the network behaves, what the IP addresses are that are used to connect. You can see the ICE connection state and how it changes from checking to connected, then completed, and that allows you to understand the network behavior of your application. You also get the statistics on the right, and your application can get the same information that is displayed there with the GetStats API. It shows you things like whether this is the active connection that is used currently. It shows you the IP addresses. However, this shows a GOOG local address. Don't use any stats prefixed with GOOG. They might change any time without notice. And it shows you the remote IP address as well. And for example, it shows you number of bytes received, number of bytes sent, and number of packets sent. And you can measure how the application is behaving on the network. And at the bottom, you get a lot of statistics graph, which basically poll gets stats every second. And you extract the metric from that, like bytes sent. And you make a timeline graph, which has the time on the x-axis and the value on the y-axis. And for example, here you can see the number of bytes sent per second and the number of packets sent per second. It's all nice and stable, 1.6 megabits per second, and about 200 packets sent per second. There's no big variation here, so it's flowing nicely. That was a local host connection, so no packet loss. And you can also see, for example, the GOOG encode usage percent, which is a measure for the encoder CPU usage. And if your users were reporting that their fans were spinning, that is a graph to look at. And another example is here, for example, the frame rate input from the camera and the frame rate sent on the network. That should usually be the same unless you have bandwidth adaptation, because your bandwidth was not sufficient, or the CPU was not sufficient to send that frame over the network. So basically, there are 3 steps when debugging something using WebRTC internals. The first step is to get a dump. Second is reading it, and the third is importing it somehow. And I'm going to walk you through that process. So first, you navigate to the Chrome WebRTC internals page, and then you click on this create dump, and that gives you a number of options. The second and third are quite important when you need to file a bug. They get you dumps that the Google developers will ask for, because it allows them to understand the behavior of Chrome much better than what we can get from JavaScript. And what is more important for you is this button, download the peer connection updates and stats data, which gives you a big JSON file usually. And you can interpret that yourself, whereas even I don't interpret the other two usually. And it gives you a big JSON file which contains a lot of information, and good luck if you want to read that yourself. I sometimes do that. I try to explain it in bug reports, and nobody can follow me then. And you can import it. I have a tool written for that. It's on GitHub. It's open source, which basically takes this dump, re-imports it into a web page, shows the very same information that we have on WebRTC internals on purpose, because we have this quasi-standard here, and it adds the ICE candidate grid from Firefox, which is not on Chrome's WebRTC internals. That is useful quite often. And so one nice thing, it shows me by the green fields here whether the connection succeeded. If it fails, it will show me a red ICE connection state change. So I don't need to expand all of these states and then look at them. Saves me 20 seconds per day. So calls failing. The typical thing to look at is the ICE connection state change, and you're looking for a value of failed there. And if that happened, you should check whether you're using turn servers, as Chad said you should, and whether you're getting relay candidates, both in the on-ICE candidate and the at-ICE candidate calls. And a relay candidate basically looks like this. The important thing here is the type relay. And I have a whole talk on that, 20 minutes. And you should get those candidates from both sides. If not, something is happening in the network. UDP might be blocked, TCP might be blocked, and the user can't get out in any way. And another thing that Marcio already said, people don't hear each other. It happens quite often on OS X and Windows, And the issue is that if you send your laptop to sleep too often, Chrome can't open the microphone anymore. You don't get a signal from the microphone. And you can see that in the statistics. So here we have a timeline graph, 110 seconds. On the y-axis, we have the audio input level here, which is 0 the whole time. That could be perfectly normal if your microphone is muted. More importantly, there are no packets sent for that period, and that is not normal. And you can get that from the getStats API. So you're calling PC getStats, and then you're dealing with the result. You're looking for a report which has a send in the name, and then you are looking for a Chrome-specific report type SSRC, and the media type should be audio. Then you're parsing, because Chrome stats are a little behind the spec, the report.bytesend and check whether it's 0. And if you do that, you can show a warning to the user. And we got a lot of complaints about this issue. We see it in about 2–3% of the calls, which is very bad, but Google is going to fix it next year. And after we showed a warning to the user and recommended that they restart the browser to reset the application state, the complaints dropped to 0. If you want to read more, there's a blog post about that. So something we saw in February was a very large desync between audio and video. So it was no longer lip sync, which is very annoying. And I was working for TalkBox at that time. We got a customer report, audio and video are desync. Then we tried to figure out how to measure that. And after some hours, we found this Goog target delay millisecond, which describes an intentional delay on the video to sync up with the audio. And, well, we saw this graph and we thought, should this increase in this linear way over time? And we thought, nope, and we found a bug. And it turned out to be an issue with specific cameras where the timestamps were off and this desync was growing. It was pretty severe in Chrome 47, and Google fixed it very quickly after they could reproduce it, and the bug fix got back all the way to stable. More about that URL if you're interested. So the quality is still horrible after you fixed all those things. So I'm going to show you some examples of what to look for. For example, if you look at the throughput, you can see here a graph showing the packet loss over time, and you can see the packet loss is cumulative, and you can see 4 events where there was packet loss. And typically, in those cases, the bandwidth adaptation will reduce frame rate and resolution, and the user perceives that as blocky and bad video quality. You could also have the packets lost being continuous, like in the blue line, and it happens as well. It is different kind of packet loss, but you need to deal with both. And if you look at, for example, the jitter, which you can see here, same graph for the same call, we can see huge spikes in the jitter. Typically, if the jitter is basically smooth and you have little variation, low variance, it's good, but those spikes are really bad. That was about 2–3 seconds in that case. And round trip time, Varun talked about it. If it's smooth, it's good. If there are spikes like this, it's bad. And that was 2–3 seconds, and that is really bad. And 100 to 400 milliseconds are acceptable depending on where your calls happen on the globe. So another thing to look at is usually the resolution and the frames per second. So we can see here that there was an issue in the call. The blue line shows the frame rate over time, and at this point it drops and stays low for 1.5 minutes. And at the same time, the number of frames sent went down. So during that period, basically there was not enough bandwidth to send the frames over the network. And in reaction to that, Chrome first dropped the number of frames per second, started dropping frames to reduce the bandwidth, and then reduced the resolution. And yeah, what you can also see in that case is that the CPU usage drops a lot when the resolution goes down, because the encoder has less frames to process and less bytes to process. Another thing to look at is the bandwidth estimate. So in WebRTC, the bandwidth between the two peers is continuously estimated, and you want to know how much bandwidth is available. And what we can see here is that the call started good, and then went to a bandwidth of about 600K, and then suddenly there's a drop here to 40K. And it starts ramping up to 600 again, stays there for a second, and then drops down. Ramps up again, drops, ramps up, drops, ramps up, is stable for a while, and then drops again, and ramps up. And that kind of behavior is going to be very annoying for users, because what happens then is that the video quality reduces, and it is perceived as bad. So it's caused by latency and packet loss usually, and will result in bad video quality. So that call was not a very good user experience. I don't want to be on that call when that happens. So WebRTC internals is a great tool. However, there are some limitations. And the most important one is that you need to ask the user before things happen to have Chrome WebRTC internals open and then send it to you. So when we had this desync issue, we couldn't reproduce it locally, and it took us 2 weeks or more to get it done from the customer who reported it. So then we started doing a thing to automatically collect that data for each and every call. We open sourced it. It is available on that URL. It is a joint project between us and TalkBox. And you just include a single line of JavaScript before any of your WebRTC stuff. So it's just a single line, no integration. You can have a deeper integration if you want to, but it's optional. And it transparently modifies all the WebRTC APIs, and it inserts itself into them. And that way you can create the dumps like you have from WebRTC internals for all sessions that you run, which can be quite a lot of data. And you send all the API traces and the getstats data to a server. And then you can really figure out what is going on. And as a summary, when the customer support person is going to ask you what happened, now you have the data to answer. And the data is the API traces and the getstats data. And you can try to figure out what happened in the call. Most of the time, honestly, it's just bad internet. There's not much you can do, but there are some cases where you're doing something wrong, like not running turn servers, and you can figure that out. And if you spend that time, your users will in the end be happier and use your service more. And your service will grow, hopefully. And with that, thank you.